Hello, my name is Jarek Ruzinski. I'm the CEO of Transmission Dynamics, company which is leading the project which is dealing with the optimal sensor placement for the future wind turbines. The project is a bilateral collaboration between the USA and the UK. At this side of the pond, we have three organizations contributing: Transmission Dynamics leading the project, and we have also OREC Catapult and the Unisys. OREC Catapult are European largest wind turbine test center and the research and development center, and Unisys are the company who've got appetite to develop digital twin for the future wind turbines. And on the other side of the pond, on the US side, we have the group which is led by Tufts University, group which is headed by Eric Hines. So we've got this collaboration which has started now more than a quarter ago, a collaboration which resulted in a very fast deployment of a number of sensors at this side of the pond, sensors which are placed at on the Levenmouth wind turbine. It's a wind turbine which was made available by OREC Catapult for the very purpose of using the new sensors and testing, effectively becoming not only a fully operational wind turbine, but also wind turbine which becomes a proving ground for the new technologies. So I'll be talking about the wind turbine monitoring solutions here, and I will very quickly start from the transmission dynamics mindset here, where we are developing bespoke intelligent sensors. Now, the element of this bespoke and intelligent sensors is very important, because we are not just recommending using sensors where the output from those sensors is recorded on some form of data acquisition system, but the sensors which have the degree of intelligence, sensors which can at a minimum perform some computations like detecting maximum value RMS, maybe even calculating fast Fourier transform, the sensors which in ideal conditions should really become our self-learning future tools for the future development work. Now, that data analytics on both of those sensors is very important, but it's supported by the preferably wireless data transfer. That wireless data transfer, again, we believe would be forming the future of wind turbine condition monitoring, because the batteries become so much more powerful, the power generated or required for those sensors to operate, even with a significant degree of onboard analytics, becomes less and less demanding. And as a result, we've got the potential of sprinkling, developing huge amount of sensors if we want to, with a very little effort. So then our mindset is to embed in those systems human-derived engineering analytics. There is just no point of pretending that we don't know what is the tooth contact frequency and trying to calculate tooth contact frequency based on machine learning, for example. We can perform the FFT, we can calculate the fast Fourier transform, and that is already a good starting point. We can also embed our know-how in those sensors, know-how related to the frequency composition of the signal which we are measuring, know-how related to the potential influence of parameters like pitting formation, scuffing, potentially even tooth breakage, the information about the torsional and natural frequencies of the system, information about the bearing characteristic frequencies. Now, it is only when our know-how is all exhausted, and it's obviously a subject of continuous development in the future, we recommend to embed in those sensors and the entire strategy of data acquisition and data monitoring artificial intelligence and machine learning. There is a difference between the two, obviously. Machine learning is effectively continuously improving computer code based on the past data which we recorded, and that process is kind of relatively simple. It's far more difficult to embed in those systems what we call today artificial intelligence, where we inject in computers those elusive elements like perception, planning, which is not as easy to pre-program, and that element of embedding artificial intelligence is getting some traction these days. And finally, all that information, all data acquisition and analytics is very often performed in cloud. So I'll be talking also about the cloud-based data analytics. Now, we've got an abundance of sensors available for us today. This is just an inset showing number of sensors, from strain gauges to temperature recording sensors which are measuring load intensity distribution, measuring load vibration, measuring bolt tension, measuring load intensity distribution across the face width of the gears, to very simple sensors which measure just the state of operation, whether the machine is running or not running, whether the machine is operating at what speeds and generating a certain amount of power. We must remember that when we are looking at the SCADA system, SCADA systems are fundamentally important input to our project. Clearly, they are already there. All wind turbines are equipped with the SCADA system. So our mindset is not just using those sensors which we have available these days, but trying to see how many of those sensors we can effectively eliminate rather than introduce to the system, which is effectively saying that we need to derive number of sensors which would be forming this minimum assembly of sensors supported by SCADA, where the machine learning process would be effectively saying there is a certain sensors which we just must have. An example here would be to measure torque reversals on the input shaft, where the SCADA system is not good at it. Torque reversals can really be directly measured only by measuring torque reaction arm stresses, or maybe directly measuring torque transmitted through the input or output shaft. So the instrumental part of our operation was the Levenmouth instrumentation deployed on the OREC Catapult asset, which is the Levenmouth wind turbine positioned at the borders of Scotland. Now, in there, we very quickly and very efficiently, during effectively the first quarter of this project, deployed a number of sensors. Some were already there, like bolt cap modules, which are measuring tension of the bolts. On this inset, we can see the bolts which are M72 bolts used in transition pieces, and then we are measuring tension directly. On the left-hand side inset, we can see the concept of SmartBugs. Those at the bottom left corner form the buttons. They're not much bigger than the code buttons which are equipped with the batteries, wireless data transfer, and the onboard analytics. At the top inset, we can see the battery pack, and then the square bags, which have significantly more processing power, including potential of measuring and calculating rainflow counting. So what we started with deploying those sensors to measure overturning moment. And this slide here shows the position of the wind turbine in situ. Position of the sensors is shown on the right hand side, where we see the red dots. That's just above the transition piece, where we have the strain gauges deployed. Strain gauges which are deployed as shown in this slide within those circles on the structural support of the wind turbine tower. We placed the strain gauges. Strain gauges were placed in the X and Y directions to measure overturning moments. Within those bugs, we also have a standard triaxial accelerometer and also triaxial gyroscope in case we wanted to use it. Now, a battery pack here is relatively large. By installing the battery pack and the gateway, we became completely independent from any instrumentation or recording instrumentation on the wind turbine itself. So gateway would collect us to cloud, and cloud-based analytics would typically take over. And the results we've started to measure from those sensors are shown here. So the system allowed us to identify frequencies, very low frequencies, 0.15 Hertz, 0.33 Hertz, which is tower first bending mode, 0.45 Hertz, which is the blade passing frequency. On the left-hand side, we can see some data which is effectively showing very high integrity and fantastic signal-to-noise ratio. Next slide here shows the complexity of the data, which is plotted against the information achieved from the SCADA systems. You can see that XY sensors are effectively allowing us to calculate the total overturning moment, and they are very nicely related to the power of the wind turbine, rotor speeds, wind speeds, nacelle orientation, and the blade pitch, and that is being studied. The next slide here shows the system used for the correlation analysis between the structural behavior of the wind turbine and various operational conditions. For example, on this occasion, nacelle orientation from 0 to 360 degrees C on the right hand inset between 200 degree and 300 degree rotation. You can see how the values of oscillations of wind turbines are filtered and how they depend on the nacelle orientation. Now, next slide shows the on the left-hand top insert, we see the X and Y strain overturning moment measured by strain gauges, plotted and showing perfect, nearly perfect in-phase response of the strain gauges. When we have the in-phase response, where the peak from the X and peak from the Y directions is simultaneously occurring, that means that we develop in-plane oscillations. Now, the lower inset shows the completely out of plane oscillations. That is exactly when we are seeing effectively orbiting mode of the wind turbine tower, and the inset on the right hand side shows how quickly we can change from in-phase to anti-phase oscillations. You can see that within 30 seconds the turbine may develop orbiting versus in-plane motion or vibration. Most interesting data. This slide, number 5, number 5 shows system which is enabled to measure the fatigue of the supporting structure, evaluate that fatigue of the supporting structure. So effectively we are looking here at the rotor speeds, and then strain oscillations amplitude is measured here versus the pitch, blade pitch angle. On the right hand side you can see again the complexity of those signals. I won't be actually discussing that in too much detail, but you can see how the change between the blade pitch from 0 and eventually pitching to 20 degrees or so results in increase of oscillations and increase of the DC value of the wind turbine overturning moments. Now, on this slide here, you can see the transient overturning moment. All of those events captured within the certain time. On this occasion, on the 21st, 22nd and the 23rd of October, you can see the number of those events where we can observe the sudden change of the DC stress level followed and preceded by a certain degree of oscillations. On this slide, we can see the example of sustained oscillations. You can see that on the left-hand top inset and the right-hand top inset, we can have the oscillations which are continuously present. In fact, all of those graphs show perfect in-phase oscillations of the wind turbine tower, indicating steady state of behavior of wind turbine tower. Next slide here shows the opposite events, where we have the transitions between in-phase and out-of-phase oscillations. Quite extraordinary events can be seen at the bottom right-hand inset, where we see the transients or burst of oscillations, which are followed by the quieter operation. On this slide, we can see the classical example of the rainflow count. Rainflow count is used when we are calculating close fatigue cycles during normal operation. We don't have to acquire all data and calculate fatigue cycles based on the single pass method. Within those squared bags, we have continuously operating system of calculating and classifying closed fatigue cycles in the form of range versus mean, or mean versus range on this occasion, where we could see that there is a very large number of cycles with a very small range of oscillations, and then less and less number of cycles is recorded with a very high range of oscillations. Clearly in fatigue analysis, it is those cycles which exhibit very high peak-to-peak value of significant more importance from the potential of causing fatigue damage, which are included here. Now, that data is then directly related to the combination of data analytics and final element modeling. Final element model of the wind turbine tower shown here allows us to do simple correlation between the values of strain measured, values of overturning moment, which we calculate as shown here, and then correlate that with the positions of the highest stresses. We may see clearly highest stress levels, not necessarily at the points where we deployed our sensors, but that's where final element methods and final element modeling kicks in as a powerful way of evaluating fatigue life cycles. On this slide, we can see the fidelity of the measurements. The bottom right-hand graphs shows the high frequency vibrations superimposed on the lower frequency vibrations. On this occasion, we are seeing the Nacelle square bug, which is measuring the stresses at the bottom of the wind turbine tower, and then that's compared with the top and the bottom of the tower measurements. And then finally, we are talking about the speed at which we are deploying those sensors. You can actually see here this blurb showing the concept of sprinkling those sensors, effectively arriving with a bag of those sensors and deploying those in various locations in the form of very simply glued accelerometers and sensors, which is shown now in the section where we discuss the deployment of the sensors in the Nacelle for torque measurement. So this slide here shows the battery, the square bug, shown as an orange box just below the battery enclosure, and then on the right hand side you can actually see the position where we installed those sensors. Now, Levenmouth wind turbine is more complicated than most of the wind turbine which we normally deal as, because we don't have this classical access to the input shaft. So what we needed to do here is we needed to perform the final element modeling and calculate torque-induced stresses, which are inducing torque-induced stress on the torque reaction flange. Is a circular disc opposed to classical torque reaction arms, or measuring directly torque on the rotating shaft. Now, the results here again show this very interesting composition of signals. On the left-hand side, you can see, for example, that the frequency of approximately 4 Hertz, we've got a high frequency oscillation. On the right-hand side inset, you can see that at 4 Hertz frequency, we have very little oscillations. In the middle inset, the second graph from the top shows exactly the same situation. Measured the signal is effectively on the same day, just spaced within 1 minute almost of the recording, and you can see how rich the signal is in information. High frequency was measured at 11:36 on the 4th of October, and at 11:37 there is very few traces of the high frequency component. The next slide shows a very interesting usage of the torque measured by using those strain gauges. We are effectively able to measure the center frequency, which is the first torsional vibration of the rotor on the flexible gearbox and the shafts and the generator. Now, this allows us to use what we call half power method, where the damping ratio, which is understood as the damping divided by the critical damping, can be calculated as shown here on this graph. Now, we can now analyze the amplitudes of the oscillations as an AC component, and the amplitude of those oscillations as the DC component. So effectively not oscillations, but the value of torque as a low frequency or DC component. You can actually see how we are forming this mindset of creating the concept of peak-to-peak wind speed as the measure of gustiness. So here, the peak-to-peak wind speed is plotted from 0, when the peak-to-peak of the wind speed doesn't change, up to 10 meters per second, which is defined as the change of the wind speed of 10 meters per second occurring within just 1 minute time. And you can see that depending on this gustiness level, we are seeing significantly higher vibration level when we actually detect the signal or measure signal during gusty wind conditions, opposed to those cases where the wind is much more steady. Now, next slide, torque reversals. Torque reversals occupy a very special attention in the monitoring and the troubleshooting and trying to understand the potential failures of wind turbines these days, because from our experience we found that very rarely we can really fully understand failures if we model the systems as it is. Obviously the systems are designed, the wind turbine tower is designed, transmission system is designed to cope with the duty cycles. So it would be not very surprising if the gearboxes are performing well when they subjected to duty cycles we believe are happening. But it is the case where in many troubleshooting sessions we found that the failures and the issues with bearings, potentially gear elements, are not necessarily caused by the steady operation, but in most cases very unique operation in terms of potentially resulting in the torque reversals. So on this inset here we can see the graphs on the top right hand inset. Black curve is showing the speed of the wind turbine during startup. We're starting at 0 speed and gradually climbing up to the speed measured on this intermediate shaft as constant when we effectively assign the wind turbine to the grid, and the red traces are showing the torque. And what we can see, especially at the lower graph here, that we assigned the wind turbine on this occasion just slightly prematurely. If we waited this extra few seconds, we could have connected the wind turbine, which is generally gradually accelerating to the synchronous speed with the grid, and then on this occasion we actually connected the wind turbine just slightly prematurely. What that really means is that instead of use of wind turbine generating power and sending that to the grid, it is the grid realizing I'm running at 50 Hertz, I'm not going to change my frequency, my inertia is actually too high, my 50 Hertz will never be changed. When you're connecting now and you're running too slowly, then it is the grid which will effectively inject the power into the wind turbine to effectively rapidly accelerate the wind turbine output shaft and the generator to the synchronous speed. During that very process, you can see in the bottom graph, significant oscillations may occur, and this torque reversal is very unhealthy in terms of operation of the bearings, not so much gear elements. On the next slide, you can see the wind turbine survey. You can see that surprisingly there is a significant number of wind turbines suffering from torque reversals. Here we've got the GE1 and 1.5, GE1.6, Vestas V82, Siemens 2.3, Gamesa G87, Micron 750, Nordex N54 and Mitsubishi 600. They are all exhibiting the significant occasionally and sometimes sustained torque oscillations during transient conditions. On this occasion it will be shut down. On some occasions it will be effectively start up when we assign the turbine to the grid. And what is happening during that process is shown on this slide here. On the right hand side, that little inset explains it all. rolling elements in the bearings, when are preloaded in one direction, on this occasion vertically down, will transfer and carry the entire load. Rollers which are at the top of the shaft don't carry the load. Due to the small clearance between the inner and outer rays, we can actually see this transition where the rolling elements gradually enter the loaded zone, and then they have time to realign between the inner and outer rays, and then they carry the load uniformly. Imagine the situation when that load rapidly changes direction and the shaft now is lifted instantaneously up with the full load applying the squashing the rolling elements which are at the top. Those rolling elements which are operating in the unloaded zone, they are misaligned. They don't have time to align, and this is actually beautifully represented on the inset on the left hand side, when we can see the measurements of the roller alignment measured with the eddy current probes which are inserted through the cover and just targeting the face of the rolling elements. You can see the left hand inset which is showing perfectly aligned bearings, rolling elements from 1, 2, 3, 4. The gap between rolling elements obviously is when the eddy current probes, non-contact displacement transducers, don't see the target, but the inset at the bottom shows the same measurement, but when the rollers are significantly misaligned. So the top graph is actually showing those rollers which are effectively at the bottom on the right hand inset when they are in the loaded zone. The left hand rollers are in the unloaded zone, and it is exactly where torque reversals would cause significant increase of the hertz and stresses well above the permissible contact pressures and contact stress levels. This graph shows another measure of the, on this occasion, quite a sophisticated system deployed occasionally to measure load intensity distribution across the face width of the gears. Here we are deploying 8 or 16 strain gauges across the gears. Those strain gauges are fitted in the root, and they are effectively showing the load intensity distribution across the face width. On this occasion, we've got the slightly higher preload on the left-hand side of the face width than on the right-hand side of the face width. But the measurements, those measurements are relatively simple. They are following the method A by strain gauges prescribed in ISO 6336, where the gauges are fitted in the root of the gear, and we are measuring peak-to-peak stress level as we are going for the transition from tensile to compressive load level, and we simply plot the peak-to-peak from the left to right-hand side of the face width, achieving that. Now, those measurements are not performed during this bilateral collaboration, but we need to dwell on those. We need to dwell on those because on a number of occasions we just don't do and provide a sufficient type testing. Type testing is never a waste of time. We deal with the companies who spend a lot of time on type testing, trying to justify the load intensity distribution, ensure that the mass-produced gearboxes released in service will not have any issues. But on this occasion, you can see the inset of the relatively famous, the Britannia gearbox, which was designed with the 4 generators attached at the back of the of the gearbox. The gearbox here is very short. The entire concept was to create a very short axial space transmission system, which is now reduced by using 4 generators, which again, the entire concept was if any one of those fails, we can still provide the 3/4 of the power, and then changing the generator in situ will be very much easier. But this graph shows it all. This graph here shows the downward helix and upwind helix of the ball gear engaging with the low speed pinion 1, 2, 3, and 4, driving those 4 generators. And you can also see here that we are plotting load intensity distribution in the form of Campbell diagram. So the red color is where we have the high intensity blue, and the intensity across the face with this lower. Also here, we are plotting something like 463 revolutions of the ball gear, which takes approximately 30 seconds, sorry, half an hour. Now, over that time, you can see that the wind speed is slightly changing. The second graph from the top shows shows that very clearly, that there is some time over certain minutes that the overall power is slightly smaller. But the graph on the right hand side bottom shows absolutely clearly the issue which costed the company significant problems, because those gears failed in service. Low speed pinion 4 was badly misaligned. They're all inserted and looked after correctly, but they all shows the same feature of being significantly misaligned. And this gear, low speed pinion 4, cannot sustain that operation. You can actually see that we've got significant preload on the upward helix side, and then we are not really getting the any preload on the unloaded side of the gear. So there is another range of sensors which are bespoke. On this occasion, I'll probably mention one of those, which is Smart Oil Plug, seen here in this inset, developed for rail applications, but can be very elegantly used in any other applications, including certainly wind turbine applications. You can see the inset here on the right hand side as an identical replica of the oil plug from the rail filler plug final drive application. Is modified, includes the battery, wireless data transfer, X, Y, Z vibration measurements, and also oil debris measurements. Now, analytics on board allows to provide the fast Fourier transform directly on board of that sensor. And then when we do that, you can see the engineering mindset, how big progress we are making with the onboard analytics. On this occasion, you can see the tooth contact frequency. This component on this occasion 400 Hertz, then higher harmonics and the next harmonic. But what is interesting when we see this graph is the number of sidebends. Sidebends are those peaks, vertical lines surrounding tooth contact frequency and the higher harmonics, and that is effectively very often used to predict the amplitude or phase modulation. Amplitude modulation is where we have bent shafts or once per revolution components, missing bolts in the coupling, for example, eccentric gear. And phase modulation is when we have a increase or decrease of pitch of the gear, which is occurring where we have the torsional vibrations. So we can detect not just those high amplitudes of tooth contact frequency, high harmonics, but detect the outliers. Outliers shown here are detected not necessarily based on the higher amplitude of vibrations in time domain or in frequency domain, but the changes in the higher frequency components, which may be just as well buried and not visible as the high amplitude of vibration. And this is occurring, for example, where we deviate from the standard involute profile because of the initial onset of the pitting, when we modify involute profile of the gears, taking apart obviously our intentional deviations from the involute profile, like tip or root relief. So gearbox validation data, if we look at that, we can also look at the Nacelle round SmartBugs, looking at the gearbox, targeting the gearbox with the sensors. So this slide here shows on the left hand side inset of the sensor. You can see that this is not very much bigger than the button of the coat. On the right hand side you can see the spring loaded clamp magnetically attached on this occasion, only for the duration when the adhesive sets, so we can very quickly deploy those sensors in a number of locations. On this occasion we actually developed some 74 channels of measurements. They were deployed within single shift, which is just the exercise which is unheard of by a large margin. You can see on this occasion the red arrows showing here showing locations and positions of the bugs, which were strategically positioned to be effectively adjacent to the existing sensors, so we can correlate the data between the existing sensors too. And here we are. We've got the SmartBug data on the left-hand side. You can see the very strong amplitude modulation. You can see the tooth contact frequency being a carrier frequency modulated with a modulation index nearly 100%. And then when we look at the frequency spectrum on the right-hand side, you can see those sidebands, and on the left-hand side, you can see the amplitude of modulation, which is occurring on this occasion at a frequency much lower than the carrier frequency, 5.6 Hertz. So, when we have the very heavily modulated signal as a carrier frequency, and the amplitude modulation is reaching around 100%, so when the amplitude goes to a maximum and then diminishes nearly to zero and goes to the maximum again, the frequency spectrum of the 100% amplitude modulated signal is such that we see the right and left hand sideband where the carrier frequency, tooth contact frequency on this occasion, diminishes and disappears completely. So we can only see the sidebands in this application. Now the multiple sidebands are typically a characteristic of phase modulation, so it's good to remember that. And then we can see the evaluation of tooth contact frequency looking at the sidebands on the right hand side, quite a rich signal at 1500 Hertz as a strong amplitude, but you can see that the entire spectrum is just scattered by equally frequency-wise distributed peaks. So what do? We can actually provide the analytics shown in this graph here, in this inset here, where we can use those signals to calculate bearing characteristic frequencies. So the equation given on the right hand side allows us to calculate bearing characteristic frequencies. So if the feature or the large pit forms on the rolling elements, we can see the frequency of that event. When it forms on the inner or outer race, we can also provide very accurate frequency of that feature happening. Now, as far as the gear elements are concerned, we very often try to demodulate the signal to decide how much of the modulation is caused by amplitude modulation, bend shaft, eccentricity, which we've discussed earlier, and how much is caused by the torsional vibrations. And that's where the Hilbert Transform comes extremely handy. What we do here is a single signal, which is just an amplitude of the signal in time domain, can be actually calculated as an FFT signal, and when we have the FFT coefficients rotated by 90 degrees, we can actually calculate the inverse Fourier transform and calculate the magnitude of the envelope of that signal. So this is amplitude modulation, and in fact when we extract the angle, phase angle effectively decides on the measure of the changes in the frequency signal of the signal. So if we have the increase and decrease pitch at certain frequencies, it is the phase which will be responding to that. And that is actually shown on the next slide here, the classical effect of the Hilbert transform, where we have the top signal very heavily amplitude modulated, and then we perform the Hilbert transform, and then the analytic value of the Hilbert transform, which is the witness, effectively the forming the information on the enveloping and the phase, as we said, on the torsional vibrations. Next slide shows another exciting part, which is the wireless bolt tension monitoring. We have those already installed on the Levenmouth, and this is shown on this slide here, where we could see those little bolt cap modules. Those are very heavily now exploited in the United States, in both America, represented by the Copper State bolt and nuts company, which are effectively attempting at the moment very successfully deploying the mindset of instrumenting just about every larger bolt which is provided to industry these days. The cost of the instrumentation is significantly reducing, and our intention is to actually avoid the incidents like those shown on the right hand side, where we have the wind turbine collapsing just due to the reduction of the bolt tension. We know that this is quite a critical aspect of operation, long-term operation of wind turbines. We know that the cohorts of technicians are typically deployed on annual basis to recheck the bolt tension, but obviously no check is carried out between the inspections. So for the 12 months we don't know what is bolt tension. On this occasion we actually measure bolt tension every 2 hours, and the snippets of that information are going to cloud and are beautifully reported, and you can actually see the implementation of that technology here, how we can use the bolt tension measurement to during the bolt installation, as well as showing on this inset here, showing the installation of the wind turbine, Levenmouth wind turbine. The lower graph is a classical example where sometime in September 2019 the bolt is tested, extended, stretched in the laboratory, and then the initial installation is shown here in October time, where the bolt tension increases to 1500 kilonewtons, only to see that over a few months time, as expected, bolt tension just gradually reduces due to relaxation, and this is why following 3 or 4 months time we actually come to retighten those bolts, and you can see the effect of the retightening carried out in May 2020, following which the bolt tension maintains the constant value, and it actually maintains the constant value up to now. In fact, there is a public trial where you can enter the Levenmouth wind turbine the monitoring and then inspect the bolt tension of those bolts with the latest information updates only 2 hours before the check. So I will finish that section with the information what's in the pipeline. Ultrasonic sensor. This is effectively trying to deploy the ultrasonic shear waves as the guided waves, waves which will be traveling along the jacket structures to the bottom of the sea, and then we are investigating reflected signal, ultrasonic signal, and this is all conducted to detect any changes in the structural integrity, like material corroded, material thinning, any potential issues with the welds. So the mindset at the moment is very important, because we are now deploying vast numbers of offshore wind turbines, and obviously with a design life of whatever 30 years, those will have to be cleared from the bottom of the sea, and between that time and now, say 20 years down the line, there will be a vested interest in to really investigate structural integrity. So what we are doing here, we are deploying this. You can actually see the real jacket structure on the left hand side. You can see the scale of it, and they are not the largest jacket structures available today or designed today. And on the right hand side, we are just taking ownership of the model of the jacket structure with exactly the mindset of using the guided wave technology, which will be deployed to investigate the ultrasonic wave propagation and reflections. So we are now effectively deploying very low cost ultrasonic pulsar and receiver units, shown here and in this slide as well from the back, very modular design. And in this slide we see the foils which are designed, effectively coils which are designed embedded on the flexible foils, which are placed usually on the magnetostrictive patches, allowing the ultrasonic guided wave deployment and reception to monitor those structures, and not only jacket structures but also wind turbine towers. And the last slide before I finish this presentation is our mindset, which was based on some input from the key stakeholders and the contribution of industrial advisory. When we're talking with some of the colleagues from GE, they mentioned that there would be obviously interest to measure torque on the input shaft of many of the wind turbines, but the cost of the telemetry system is indeed prohibitive in these days. So to overcome that problem, we took that advice on board, and we are now in the process of designing something which we'll call killer bugs. Effectively, they are not much bigger than our SmartBugs, but they are equipped with the strain gauge positioned at the very bottom. You can see the two magnets surrounding the strain gauge, battery supply, wireless data transfer, and a very simple kit to clean the shaft and apply the bug, and within 15 minutes even technicians who never had the experience with the strain gauging could deploy very successful torque measuring devices, which can live there for a number of months before the battery is depleted. But over that time, say a year of operation, there is a significant advantage because we can measure histogram of load, we can detect the torque reversals, and we can just run through the maximum minimum oscillations of torque, which are not necessarily captured and handled by SCADA system. So, summary. So far, we have this fantastically developing mindset of creating this abundance of sensors with a mindset of reducing that number to the minimum for the recommendation of the future wind turbine placement. So far from the sensors we are deploying, we have excellent data quality, very high resolution, high fidelity, high signal to noise ratio. They deploy and form the standalone systems. As I mentioned before, we're able to deploy using the mindset of sprinkling those sensors with the wireless capability. We're deploying 74 measuring channels, which was completed within 1 day. We are measuring hub rotational frequencies. We are detecting blade passing frequencies, tower natural frequency, blade flap wise frequency has been also detected and fully quantified. We are detecting already fairly high magnitude of oscillations of the wind turbine, and obviously measuring this overturning torque, overturning moment. We are directly going to use that data to evaluate structural integrity of the jacket structures. Then the system can be also used for the fundamental research in turbine dynamics, condition monitoring, and obviously for the evaluation of the remaining asset life. So this is everything from me. Thank you very much. We are hoping that you will join us in the future presentations as the project progresses, where we'll be reporting on the ongoing outcome of that work and ongoing involvement of machine learning and establishing digital twin technology, which is very heavily exploited also at the Tufts University and the colleagues on the other side of the pond. Thank you very much for your attention. If there was any interest to obtain more information, copy of the presentation, drop us a line. You can contact us on www.jrdltd.co.uk or contact any of the team members mentioned in this presentation. Thank you very much for your attention.